There is an organ inside you that has been quietly rewriting its own operating manual every single night for the past 60 years. Not dramatically, not in the way that transformation usually announces itself, with symptoms, with signals, with the kind of biological event that commands attention and demands a response. Quietly, incrementally, in the language of cellular adaptation that runs beneath the threshold of conscious experience and that accumulates across the decades into a set of conditions so different from what existed at 30 or 40 that calling it the same organ is almost a biological courtesy. Your liver at 60 is not your liver at 35. The architecture is the same. The hepatocytes still line the sinusoids in their precise formations. The portal vein still delivers its nutrient-rich cargo directly from the intestines. The bile ducts still carry their output toward the digestive system. But inside the machinery, in the enzymatic systems, in the mitochondrial density of the hepatocytes, in the speed of cellular regeneration, in the capacity to manage oxidative stress, in the rhythm of the metabolic cycles that govern everything the liver does, something has changed. Several things have changed, and understanding what has changed and why is the foundation of understanding what eating once a day does to the liver after 60 in ways that most people and most physicians were not expecting. Travel inward, past the rib cage, into the upper right quadrant of the abdomen where the liver sits, dense and dark and extraordinarily complex, performing more than 500 distinct biochemical operations simultaneously while the person it belongs to goes about their day without a single conscious thought directed toward it. At 60, the liver has shrunk slightly from its peak volume. Hepatic mass typically declines by 20 to 40% between the ages of 40 and 80. A reduction driven by a decrease in the number of hepatocytes and a reduction in hepatic blood flow that approaches 40% in some individuals by the 7th decade. Less mass, less blood flow, less enzymatic throughput per unit of time than the liver managed with seamless ease at 30. The organ is not diseased, it is aged. And aging, in the liver as in every other biological system, means reduced reserve capacity. Reduced ability to absorb metabolic insults, to compensate for dietary excess, to regenerate damaged tissue, and to perform the extraordinary daily workload of filtration, synthesis, and metabolic conversion at the speed and efficiency it once managed without effort. Into this context, into the liver of a 60-year-old body carrying the accumulated biochemical history of 6 decades, comes a dietary practice that is doing something to hepatic biology that the research community is only beginning to map with the specificity the finding deserves. Eating once a day, one meal, a 23-hour fasting window that the liver inhabits every day, and that interacts with the aging hepatic architecture in ways that are, depending on how the practice is implemented and sustained, among the most hepatoprotective interventions available without a prescription. To understand why, you need to understand what the liver of a person over 60 has typically been managing for years before OMAD enters the picture. In the continuously fed state, 3 meals a day, frequent snacking, the modern dietary pattern that keeps insulin elevated for the majority of waking hours, the liver is almost never in a state of metabolic rest. Through the portal vein, it receives a continuous stream of glucose, fructose, amino acids, fatty acids, and the molecular byproducts of digestion, demanding continuous processing, continuous enzymatic activity, continuous insulin signaling response. In a young liver with abundant hepatocyte mass and high mitochondrial density, this continuous demand is managed with relative ease. In a liver at 60, with reduced hepatocyte numbers, declining mitochondrial function, and a regenerative capacity that operates at perhaps half the rate it did 2 decades earlier, the continuous fed state is not neutral. It is a sustained workload being imposed on a system whose capacity to sustain that workload without accumulating cellular damage has measurably declined.
The most visible consequence of this sustained workload in the aging liver is a condition whose prevalence increases dramatically after the age of 50, and that is now present in an estimated 30 to 40% of adults over 60 without their knowledge. Non-alcoholic fatty liver disease, the accumulation of fat within the hepatocytes themselves, driven by the combination of chronic hyperinsulinemia, excessive fructose metabolism, and the reduced mitochondrial capacity of aging liver cells to oxidize the fatty acids arriving faster than they can be processed. Fat accumulates not in the fat tissue surrounding the liver, but inside the liver cells themselves, displacing the mitochondria, disrupting the enzymatic architecture, increasing the oxidative stress burden on a cellular environment whose antioxidant defenses are already operating below the capacity they maintained in younger decades. The liver does not signal this accumulation with pain. It does not produce symptoms that would direct attention toward what is happening inside it. It compensates, as it always does, until the compensation becomes insufficient. And by that point, the structural damage has often progressed far beyond what most people imagined possible in the absence of significant alcohol consumption or obvious dietary excess. This is the hepatic landscape that eating once a day enters, and what it does there in the specific biochemical environment of an aging liver carrying a fat burden in a continuously fed metabolic state is one of the most compelling stories in the emerging science of fasting and organ-specific aging.
Within the first extended fasting window, as the hours accumulate past the 12-hour mark that normal overnight fasting rarely surpasses, past 14 hours, past 16, into the territory of 18 and 20 hours that OMAD structure creates each day, a metabolic shift begins in the liver that the continuously fed state perpetually prevents. Glycogen, the liver's stored glucose reserve, approaches depletion. Insulin falls to its nadir, and in that low insulin environment, the hormonal lock that has been keeping the liver's fat stores sealed begins to release. The enzyme hormone-sensitive lipase, suppressed by insulin whenever food is present, reactivates. The fatty acids that have been accumulating inside the hepatocytes, the same fatty acids whose presence defines the fatty liver condition, begin moving. They enter the mitochondrial beta-oxidation pathway, the enzymatic assembly line that dismantles fatty acid chains into the acetyl-CoA units that feed the citric acid cycle and emerge as ATP. The liver is burning its own fat stores, not through caloric restriction in the conventional sense, through the hormonal environment created by the extended absence of food. An environment the liver has been designed across millions of evolutionary calibration to use precisely this way. Here is what makes this particularly significant for the liver over 60. The mitochondria of aging hepatocytes are not merely fewer in number than those in younger cells, they are qualitatively different, accumulating mutations in their DNA, operating at reduced membrane potential, generating more reactive oxygen species per unit of ATP produced, and being cleared by the autophagic process called mitophagy less efficiently than the mitochondria of younger cells. The result is a population of hepatic mitochondria that is simultaneously less productive and more damaging, producing less of the energy the liver needs while generating more of the oxidative byproducts that damage the cellular architecture around them. Extended fasting, the 23-hour window that OMAD creates, activates a cellular process that directly addresses this mitochondrial crisis in the aging liver. Autophagy and its mitochondria-specific variant, mitophagy, are dramatically upregulated during extended fasting through the suppression of mTOR, the nutrient-sensing protein that keeps cellular housekeeping processes switched off whenever food is present.
During the fasting window, mTOR activity declines, the autophagic machinery activates, and the liver begins the systematic identification and dismantling of its most damaged mitochondria, replacing them across weeks of sustained practice with a population of newer, more functionally intact organelles produced through the process of mitochondrial biogenesis, itself stimulated by the metabolic demands of the extended fasting state. This is not a theoretical benefit. In animal models of aging liver disease, fasting-induced mitophagy has been shown to reduce hepatic fat content, decrease oxidative stress markers, and improve mitochondrial function in a way that pharmacological interventions have struggled to replicate with equivalent safety and specificity. The aging liver, given the sustained fasting window it needs to run its housekeeping cycles, begins rebuilding its own mitochondrial population from the inside.
For anyone who wants to understand the full timeline of hepatic recovery during OMAD, the specific markers that change, the sequence in which they change, and the nutritional conditions required during the single meal to support rather than undermine this process, the Body Hidden Signals Guide in the pinned comment below maps it with the precision we are working through here. It is a resource worth reading as a direct companion to what we are uncovering in this script. Now move deeper into the liver's biochemical landscape, because the fat mobilization and the mitochondrial renewal are only two dimensions of what extended fasting is doing to the aging liver. There is a third dimension that is, in many ways, the most consequential for the long-term trajectory of hepatic health after 60, and it involves a process whose importance to liver biology has only recently been understood with the clarity it deserves. That process is hepatic autophagy beyond mitophagy, the clearing not just of damaged mitochondria, but of the full spectrum of misfolded proteins, damaged cellular organelles, and lipid droplets that accumulate inside aging hepatocytes, and that the continuously fed state perpetually prevents the cell from clearing. The hepatocyte at 60 is a cell carrying decades of molecular debris, proteins that were synthesized incorrectly and never cleared, lipid droplets that accumulated during periods of excess caloric intake and were never fully mobilized, cellular membranes that have been oxidatively damaged and never replaced, receptor proteins that have been downregulated by years of chronic overstimulation and that have never had the recovery window required for their density to restore. In a continuously fed body, mTOR is active, autophagy is suppressed, and this debris accumulates continuously. In a body practicing OMAD, with 23 hours of daily mTOR suppression, the autophagic machinery runs with an efficiency and duration that creates the cellular equivalent of a deep cleaning, systematic, thorough, and accumulating in its effects across weeks and months of sustained practice into a hepatocyte population that is measurably cleaner, more functionally intact, and more capable of the high-performance biochemistry the liver was designed to execute. The clinical consequence of this autophagic renewal in the aging liver is reflected in the inflammatory markers that characterize its distress. Alanine aminotransferase, ALT, the liver enzyme most sensitive to hepatocyte damage, whose elevation in the blood indicates that liver cells are releasing their contents into the circulation. Gamma-glutamyl transferase, GGT, the enzyme most sensitive to oxidative stress within the hepatocyte and to the early stages of fatty liver infiltration. C-reactive protein, the systemic inflammatory marker that reflects the low-grade hepatic inflammation that fatty liver disease drives through the bloodstream into every tissue it perfuses. In individuals over 60 who adopt OMAD consistently and sustain it for 12 to 16 weeks, these markers show measurable improvement in a pattern that mirrors what the cellular biology predicts, declining as the fat content of the hepatocytes falls, as the mitochondrial function improves, as the autophagic clearing reduces the burden of cellular debris that was driving the inflammatory signaling. But the liver after 60 is not simply a metabolic organ.
It is the body's primary endocrine processing facility, the site where hormones produced elsewhere are metabolized, modified, and cleared at a rate that determines their systemic concentration and their downstream biological effects. And in the aging body, the liver's hormonal processing capacity has implications that extend into virtually every experience of daily life, from energy and mood to cognitive clarity to the maintenance of lean muscle mass. Testosterone, cortisol, estrogen, thyroid hormone, insulin-like growth factor, all of these are processed, modified, or cleared by the liver. And the efficiency with which the aging liver performs these functions determines not just hormonal balance, but the quality of the hormonal environment in which every cell in the body is operating. In a liver carrying significant fat accumulation, a liver whose hepatocyte architecture is disrupted by the lipid droplets of non-alcoholic fatty liver disease, this hormonal processing is impaired. Estrogen clearance slows, contributing in men over 60 to the estrogen excess that suppresses testosterone production and drives the body composition changes most associated with male aging. Cortisol clearance becomes less efficient, extending the duration of cortisol's catabolic effects on muscle tissue and contributing to the elevated baseline cortisol that characterizes the hormonal profile of chronically stressed and chronically sleep-disrupted aging individuals. Thyroid hormone conversion, the liver's transformation of the storage form T4 into the metabolically active form T3, is reduced in a fatty, inflamed hepatic environment, contributing to the subclinical hypothyroid state that produces fatigue, weight gain, cognitive slowing, and cold intolerance in aging individuals whose thyroid gland itself is functioning perfectly normally. When extended fasting reduces hepatic fat content and restores hepatocyte function through the mechanisms described, through fat mobilization, mitochondrial renewal, and autophagic clearing, these hormonal processing functions begin to recover. Not completely, not immediately, and not in isolation from the other variables that influence hormonal balance in the aging body, but measurably, progressively, and in a direction that the person over 60 experiences as a gradual restoration of energy, of hormonal equilibrium, of a vitality that had been declining slowly enough to be absorbed into the expected trajectory of aging, rather than recognized as a symptom of a liver that was not performing the functions it was designed to perform. There is a dimension of OMAD's effect on the aging liver that requires particular attention, and that requires, alongside the scientific understanding we have been building, a note of genuine biological nuance. Because the liver after 60 is not simply more responsive to the benefits of extended fasting than the liver at 30, it is also more sensitive to the conditions of the single meal that follows the fast. The hepatocyte population is smaller, the regenerative capacity is reduced, the margin between a nutritional environment that supports hepatic recovery and one that imposes additional burden has narrowed. And this means that the quality, the composition, and the timing of the single meal in an OMAD protocol after 60 are not incidental details. They are, biologically, as important as the fasting window itself. A single meal that arrives as a large bolus of refined carbohydrates and processed fats delivered into a fasting liver whose insulin sensitivity has been restored by 23 hours of low insulin exposure, imposes a metabolic shock whose consequences are measurably different from the same caloric content delivered as high-quality protein, complex carbohydrates, healthy fats, and the micronutrient substrates the liver's regenerative machinery requires. The restored insulin sensitivity of the fasted liver means that the insulin spike following the meal is larger and faster than it would be in a continuously fed metabolic state. If that spike is generated by a meal rich in refined sugar and industrial fats, the hepatic lipogenic response, the conversion of excess carbohydrate and fructose into liver fat, is amplified rather than attenuated. The fasting window that spent 23 hours clearing fat from the hepatocytes can be partially undone in the hour of a nutritionally poor single meal, in a way that the liver at 30 would manage with greater resilience than the liver at 60 can afford. This is not an argument against OMAD after 60. It is an argument for understanding that OMAD after 60 is a practice whose power lies in the pairing of the fasting window with a single meal that is genuinely worthy of the biological preparation that preceded it. Adequate complete protein, sufficient to support the hepatic protein synthesis that OMAD's fasting window stimulates, and to maintain the lean muscle mass that the aging body is already predisposed to lose. Complex, fiber-rich carbohydrates that deliver glucose slowly, preventing the lipogenic spike that refined carbohydrates produce. Cruciferous vegetables, whose sulforaphane content activates the NRF2 pathway and supports the liver's antioxidant enzyme systems during the hours when oxidative stress from the day's metabolic work is being cleared. Healthy fats, olive oil, avocado, walnuts that provide the anti-inflammatory fatty acid profile the healing hepatocyte requires, without contributing to the lipid overload that fat-infiltrated liver cells cannot efficiently process. And the micronutrients, choline, magnesium, B vitamins, zinc, that the liver's enzymatic machinery uses as cofactors in the hundreds of biochemical reactions it performs, and that the aging liver, with its reduced reserve capacity, cannot afford to be deficient in. When OMAD after 60 is practiced with this nutritional intelligence, when the 23-hour fasting window is followed by a single meal that provides everything the liver's regenerative machinery requires and nothing that undermines it, something begins to happen in the hepatic tissue that the biology had been prepared for, but that the continuously fed state had been preventing. The fat content of the hepatocytes declines week by week. The mitochondrial population renews toward greater functional integrity. The inflammatory markers retreat from the elevated baselines that fatty liver disease had been maintaining. The hormonal processing functions restored toward the efficiency they had before the fat accumulation disrupted them. The liver, which had been quietly struggling under the combined burden of reduced reserve capacity and continuous metabolic demand, finds in the daily fast something it had not had in years: the sustained, uninterrupted time and the hormonal environment required for the cellular housekeeping that its own biology has always been designed to perform, if only it were given the conditions.
Step back now from the hepatocytes and the mitochondria, from the autophagic machinery and the lipid droplets clearing from cells that had been carrying them for years, from the hormonal processing functions slowly restoring their efficiency, and the inflammatory markers quietly declining in a bloodstream that is becoming a cleaner biochemical environment week by week. Step back and hold the full picture of what eating once a day is doing in the liver of a body over 60. It is not simply a dietary practice, it is a biological intervention, one that speaks directly to the specific vulnerabilities of the aging liver with the precision that most conventional dietary advice never approaches, because most conventional dietary advice was not designed with the aging liver's particular situation in mind. The liver at 60 does not need what the liver at 30 needed. It needs fewer hours of continuous metabolic demand and more hours of uninterrupted repair. It needs the hormonal environment of extended fasting, the low insulin, the activated autophagy, the upregulated mitophagy, the fat mobilization, not occasionally, not as a weekly event, but as a daily rhythm that gives the cellular housekeeping systems the sustained, consistent access to their operating window that the continuously fed state was perpetually denying them. The liver after 60 has been working harder than it should have for longer than it needed to, under conditions that the aging hepatic architecture was never designed to sustain indefinitely.
not because of dramatic excess or obvious abuse, because of the structure of eating that modern life normalized. The 3 meals, the snacks, the insulin that never fully fell, the mTOR that never fully quieted, the autophagic machinery that never fully ran. OMAD changes that structure, and in changing that structure, it gives the liver something that no supplement, no medication, and no dietary modification short of extended fasting can reliably provide: time. Daily, sustained, hormonally appropriate time to do the work it has always been capable of doing. The work that was always running in the background of its biology, waiting for the conditions that would finally allow it to run to completion. What we have traveled through today is one of the most important and least discussed intersections in the science of aging, fasting, and organ-specific health. The story of a liver that has more capacity for renewal after 60 than most people were ever told, and a daily practice that speaks directly to that capacity in the language of cellular biology. The Body Hidden Signals Guide in the pinned comment below extends this conversation across every major system, mapping what your daily habits are doing inside your liver, your hormones, your brain, and your metabolism, signal by signal, with the same depth we covered here. If what we uncovered today changed the way you see what your liver is still capable of, that guide is where the next layer of this story begins.